So now we have the first law of thermodynamics. So first law of thermodynamics, that is just the conservation of energy. The energy balance, balance is very simple. Energy in equals to energy out. You already heard of this, or maybe you already heard of this, something like Q in is equal to Q out. That is just the same. Okay. For number one, we have the closest step, which is usually the device that is being used in a closed system is piston cylinder device, which means that mass cannot cross the boundary. So this is what it looks like. This is what a piston cylinder device looks like with in the diagram. So we have of course a piston, and we have a gas which is trapped, and of course cylinder. That's why it's called piston cylinder, because the device is shaped as a cylinder. So what happens here is the piston will just compress the trap gas. Okay, so when a trap gas or a gas is compressed, a combustion happens. That is basically it. Okay, so Q here is equal to the delta U plus W. And of course, delta U is equal to mCV delta T. So what are those parameters? So CV, that is what we call the specific heat at constant volume. Remember that. And delta T, of course, that is just T2 minus T1. Q is the heat. W is the work done. And of course, delta U will be the change in internal energy. So U stands for the internal energy. Okay. So let's have this one. So mechanical energy. So mechanical energy is just a combination of kinetic energy and potential energy. Of course, potential energy is simply the mgh. Now mg there is also the weight, right? So you can also rewrite the formula by wh, or weight times height only. Now for the kinetic energy, that is 1/2 mv squared for linear motion. Okay. Next, we have the chemical energy, which are the delta U, which is mCV delta T, that is change in internal energy, and delta H, which is the mass, times Cp delta T, which is a change in enthalpy. Now, we also have a relationship between Cp, Cv, and R. The relationship between them is just Cp minus Cv equal to R. And also for the adiabatic constant, which is K, that is Cp over Cv equal to K. Okay, so you'll be using this adiabatic constant when the process is also adiabatic process. Okay. Now for the work, we have a work is equal to F cosine theta S equal to, or F cosine theta S, where F is your force, cosine theta of course theta is the angle, and S is your displacement. Now you can also have here just Fs, the cosine theta, if the theta is equal to 0, because cosine 0 is just equal to 1. Therefore, you'll be left with Fs. Or if the motion is just directly horizontal, okay, or linear. Now, for the work in piston cylinder, that is just the integral of P dV, or the pressure dV. Or if it's a shaft work, work is equal to the negative integral of V dP. Okay, so let's have here for the heat. So we have two kinds of heat. We have sensible and latent heat. For the sensible heat, we have here with change in T, or change in temperature, but with no phase change. So what does it mean? So for example, we have a water that is let's say 40 degrees Celsius, and then it became 70 degrees Celsius. So as you can see, water from 40 degrees into 70 degrees. So water to water. So the water doesn't have any phase change. The water is still water. So but it has a change in temperature. So that is called sensible heat. Okay? Now for the formula for the accessible heat, or the Q, is equal to mc delta T. Of course, C is the specific heat. So we have here the value for C for water, ice, and steam. Okay, so I won't be reading this one. You can just take note of this one. Okay. So for number two, latent heat. For the latent heat, we have no change in temperature, but with phase change. So what does it mean? So for example, there is a water at 100 degree Celsius. So take note, when the water is at 100 degree Celsius, it's not automatically will become a steam. Okay, even though that is the uh, even though it is in 100. So what happens here? So the water will reach in 100 degrees, and it will go phase change. Okay, it will become water to steam. So what happens? It become water at 100 degrees, and then it will become a steam at 100 degree also. So as you can see, those are both 100 degrees. Therefore, there is no change in temperature, but there is a phase change. So that is called latent heat. So the formula for that is really simple. So we have Q is equal to, or the latent heat is equal to mass times the L, or the L is the specific latent heat. So for the L, we have a given here. So for water, so that when it is ice to liquid water, okay, ice, it will become water. That is called fusion. Okay, and then that's why we have values here, or the constants. So LF, that is stands for latent heat of fusion. That is 80 kilocal per kilogram, or 144 BTU per pound, latent heat of fusion. Next, how about if we have liquid water to steam? That is called vaporization. That's why we have here LV. That's 540 kilocal per kilogram, or 970 BTU per pound. So that is called your latent heat of vaporization. That is why it's called LV. Now we have here units of energy. These are some conversion factors. So we have here 1 kilowatt hour is equal to 3.6 times 10 raised to 6 joules, or 860 kilocalories, or also equal to 3413 BTU. Now we have here all units. Okay, so these all units are very seldom to appear in problems. However, I will also discuss it. So quad is equal to 10 raised to 15 BTU, and 1 BTU is also equal to 778 foot-pound. Now for units of power, of course, power is the rate of doing work, or rate of using energy. Okay, so 1 HP, or 1 horsepower, is also equal to 746 watts, or 500, or also equal to 550 foot-pounds per second, or 33,000 foot-pound per minute, or 42.4 BTU per minute. Okay, so that's it. So I think we can move on to some sample problems.